at the front desk is important for the administration to quantify our seminar. And also, you know, I also was told to remind you that at the end we have some refreshments also. And please don't disappear at the end. Please join us for conversation and wine.
No worries.
So our next speaker is Professor Chris Budd from the University of Bath. He is actually a specialist in nonlinear problems, and today he will tell us about his efforts for outreach in mathematics. Welcome and thank you.
Well, thank you very much. Well, it's a great pleasure to come here. Many years ago, when basically dinosaurs ruled the earth, I was a student here, and then more recently my son was a student here, and I have a slight qualification to talk in front of this august body because my daughter is actually a professional artist up in Glasgow, and she's always talking to me about her work and stuff. So it's wonderful to talk to a joint group of mathematicians and artists. So I sent the programme to my daughter and she said, "Looks good, Dad," she said. So, so I represent various bodies. I do a lot of outreach work with the Royal Institution and Gresham College, and my day job is at the University of Bath and the Institute for Mathematical Innovation. And on the front we can see myself, there I am, and two young men taking part in some mathematics through toys. So my talk is called A Mathematical Approach to Toys, and like all mathematicians it's generally a good idea to write down definitions before you do anything. So I looked up the definition of toys. So here's what is a toy and what's that got to do with maths. So definition one, these are all basically from Wikipedia. An object for a child to play with. I think we're all pretty happy with that. And we'll have a look at some ways that we can teach maths through that. An object regarded as providing amusement for an adult. Again, we can teach lots of maths through that. This one I'm going to come back to quite often. An object's a small representation of something familiar. And we'll see what that's got to do with maths. The next one I hope isn't anything to do with maths. A thing or matter of little or no value of importance, a trifle. But the last one could almost be a description of pure maths, something that serves for diversion rather than for serious practical use. Anyway, so there's various definitions of toys. So what I want to do in this talk is kind of talk a little bit about the interplay between maths, toys, and how we can use this interplay in various positive ways. I'll start with a kind of a quick run through of some of the ideas that I had about maths and toys, and then I'll come back and look more detail at some case studies. So firstly, I would argue very, very strongly that mathematics is often learnt through play. Okay, you take things, formulae, ideas, concepts, and you play with them. You play with them. And one of the lovely things about toys is, of course, they encourage that set of idea of play, and therefore we can do learning and teaching through that. So the Towers of Hanoi, a canonical example, something I've often used with young people to play, and they learn ideas of induction and stuff like that. Secondly, many toys involve solving puzzles. And again, how can we define maths? We can almost define maths as solving puzzles. Okay, maybe pure mathematicians might disagree with me there, but certainly my kind of maths is very much involved with solving puzzles. So here's a topology toy that we use quite a lot in our science fairs. The idea being to take the string off the loops through topological reasoning. Very famously, of course, we have Sudoku. Carol Vorderman said Sudoku has nothing to do with maths. I couldn't agree with her less. Sudoku has everything to do with maths. It's all mathematical reasoning, and there's some very interesting questions like, is a solution to Sudoku unique? And that's a great mathematical question, but lots and lots of people maybe have their first introduction to mathematical reasoning through Sudoku, and I love pointing out that Sudoku is, of course, Latin squares, and Latin squares were invented by Euler. So there we go. What's the most famous mathematical toy of all? Well, I think it's a reasonable claim to fame is the Rubik's Cube. So again, when I was at Cambridge, I came up to Cambridge in 1979, which is when the Rubik's Cube was just coming out. One of the first courses I did was a course in group theory, and we all suddenly realised, hey, we know how to solve the cube, or at least the techniques for solving the cube were being taught in our group theory class. And whole PhDs were being written at Cambridge on the cube. So it was actually for us an immensely important thing. And I know that in the audience there are people who have almost based their entire career on solving the cube. I won't mention them in case I embarrass them. Alex Bateman has produced this cube for me. And so I learnt all about alternating groups, and there's some really good mathematical questions like what is the minimum number you can solve the cube in from any configuration, and I've been informed today that this is 20. Okay, so this is a really good question, and you can learn a lot from the cube. In some cases, maths and toys can be indistinguishable. Next September, a group of us again in this room are taking part in an origami conference in Oxford, looking at the links between maths and origami. Tadashi is one of our keynote speakers. On the left, we have a toy, which is a bull moose, folded by Robert Lang. And on the right, you have a folding pattern. So if I was to show you that, people would say, it's maths, it's obviously maths, and yet that and that are equivalent. They're the same. Robert's great achievement is to work out a kind of mathematical way of getting from that to that, so that you can fold something, with 4 legs, antlers, all these spiky bits, all this. It's just astonishing what he can do. And again, Robert is one of the organisers of this conference next year. Mathematics also plays a very important role in what many of us think of as toys, which are kind of mechanical objects. Now, obviously, I've missed many of the talks this week. I've probably been on Ireland. I'll come back to that in a minute. But a toy that I've studied in my own work, part of my research, is looking at the dynamics of objects which involve friction. If anyone tells you they understand friction, I would disagree with them. Really, really complicated. And the woodpecker is a lovely example where it'll stay quite happily on a spike like that, but if you bring it back, it'll peck the spike and move downwards, and then we can use this as a way of looking at the interplay between friction and impact and motion, and that's really, really subtle. I think Keith might have talked about it earlier this week, and there's a lot to do that. So mathematics not only gives you the toy, helps you analyse it, and helps you build new toys. And finally, in this kind of brief run-through, I come back to this thing. A toy is often a small representation of something familiar, and this pretty well describes a lot of my research. So, to misquote Michael's talk, I spend a lot of my time looking at the real world, except I don't. I look at problems like climate change, where it's so complicated, if you wrote down all the equations, you couldn't possibly make any sense of it. So you construct a small representation of it, and then you study that. And that's what we call a toy model. And I'll come back to climate presently, but just to say that the study of toy models, reduced representations of big physical systems, have been intensely important in the development of mathematics and have great, great value. So, and we call them toy models. And so toys in the title, so I thought I'd mention. Just to say on the right, this Michael talked about analog computers. This is one of the first climate simulators, and it was literally a toy. It was a model where they made things out of water and spun it around to simulate the climate. Okay, so that's kind of an overview. And what I want to do in this talk is take you through some case studies of where I have personally used toys in various things. So we'll have a look at the way we can use it to teach in maths, particularly for young people. Then I want to look at some of the links between art and maths and toys. Favourite topic of mine, big toys, really big ones, chaotic toys, and toy models. And I thought I'd put this thing up, Toy Story. Toy Story, which is of course a film all about toys, was, I believe, the first film to hit the real popular market based entirely on mathematics. So all of the animation in Toy Story was done using cubic lead splines. And mathematicians, I think one of the largest employers of mathematicians nowadays is in the movie industry. And so it's a great area to work in if you want to look at the interplay between maths and movies and creativity and stuff. But above all, here's a quote I will refer to quite often. I want to show how toys can awaken our mathematical curiosity. Okay. So let's start with toys in teaching maths. Here's a picture. I'll tell you the story about this picture. I spend a lot of my time doing outreach, and what I like doing often is going to festivals of science, where you may have an audience of tens, if not hundreds of thousands of people. So it's a great way of getting maths out there. And one of the biggest festivals is called the Big Bang Fair, which they hold at the NEC in Birmingham. And we wanted to do some maths, we here being the IMA, and the organisers said, no, you can't possibly do a stall at the maths fair. No child would ever want to come to a maths stall. So there's our stall, and now so you can see no children have wanted to come at all. Okay, so this was a demonstration, and we are teaching maths, but what the young people here are doing are they're basically learning maths and engaging with the stall through toys. So we've got some in the background there, and that thing there is a chaotic double pendulum. So why do we use toys? One is essentially to capture our audience, to engage them and to get them to have a feeling of wonder. They're doing something that's amazing for them. Okay. Secondly, I want to develop this idea that maths is something that you play with, that you play around with things, you develop this kind of hands-on way of inquiring about things. And thirdly, it is actually possible, by doing all this, to teach some serious maths on the way. I mean, really quite hard maths sometimes. So let's have a look at some of the toys on the stall. So we want to look at what this girl's doing here. What this girl here is doing is looking at a packing problem toy. Apologies for the poor quality. These are photos taken with my mobile phone during the exhibition, so the quality is a little bit vague. At the Big Bang Fair, there were stalls by outfits like British Aerospace and Rolls-Royce, which cost, tens, if not hundreds of thousands of pounds to put on. That cost me £5 in Hawkins Bazaar. In fact, most of my toys cost about that amount. Good thing actually, because they tend to disappear during the festivals and have to be replaced. But what this is just a series of coloured beads that are joined together in different configurations, and all you have to do is put them in the box. That's it. Simple. It sounds simple, but it's hard. It's an example of a knapsack problem in mathematics. Knapsack problems are NP hard, and as far as I know, there's no quick algorithm for doing this. So you get the young people to do it, and they spend ages and ages trying to do it, and you can't get them away. And whilst they're doing that, you can talk to them. You can say, this is a knapsack problem. It's like putting stuff in the car or in the fridge. It's really hard, and by the way, the maths is the same as sat-nav devices. Essentially the same maths to packing around with things like that as to navigate your way through a network. If you really want to challenge them, do it in 3 dimensions. This is the Bedlam cube, where it has many names, and the idea is, again, to try to fit the pieces together in 3D. As far as I know, there is no quick algorithm for doing this. I think this is NP hard. So again, you can talk that through when they're finding problems. It is hard, except if you want to go onto this website, you can have a look at this. I'll presume these lectures will be recorded. Jasmine, aged 8, will tell you how to do it. So here are the kids. So they go off and do this, and after half an hour, they're still with you. After an hour, They may have solved it during that time. You can talk to them about as much maths as you want. The parents are happy because you've been looking after them. And you get these smiles. These are the smiles of children that have achieved the solution of the problem. There's various cases here. And they do get a great achievement. And then you say, oh, you've been doing maths. And they say, oh, I don't like maths. And you say, well, come on, you just enjoyed yourself. And they've developed this sense of inquiry. And hopefully, we produce some future mathematicians in doing this. Okay. So I mentioned earlier topological toys. Again, these are a great source of entertainment. This is the one I showed earlier. This young lady here is wearing a maths busking t-shirt. If you haven't heard of the maths buskers, they're a group of mathematicians that go around and go into places like shopping centres and wear maths busking t-shirts and accost innocent members of the public and do maths with them. At least in one case, getting arrested. That was in the Bull Ring in Birmingham. Anyway, and this, possibly for doing this, this guy's tied up with some ropes with this woman, and it's a fairly famous tie problem where you have to untie yourself. It's variously attributed. It's often called Siemens ropes, but I think it goes back much earlier than that. But again, the point about the use of toys here is that it's a wonderful way to directly engage with people where they are. You're bringing maths to people where they are. What do you learn in this? Topology and, of course, a bit of knot theory. Magic. Not quite sure whether this is toys or not, but I think it works. This is the University of Wolverhampton, as you can tell, all dressed up, again at the Big Bang Fair, teaching binary arithmetic using a magic trick. Okay, so all the kids have to do here is choose the cards where they see their numbers. You add up the top cards at the top, and it's binary. But you can teach binary arithmetic, bit of number theory, and so on through the medium of magic. And again, magic is a very, very good way of engaging young people, and they can then go off and do the tricks to their friends, and that makes them cool, which is good. You can do other things. You can do probability, and you can do other types of maths. I'm sure you recognise this guy. It's David Spiegelhalter at the Cambridge Science Festival using toy dice to do some probability. And then here's me again with this young man. And what we're doing here is a card trick based on modular arithmetic. And I just love his smile in that picture. Don't tell me that maths isn't fun. Okay. So that's the way we use toys in kind of an immediate way. But another form of the outreach we love doing, and again this is very, very related to this audience, is showing the links between maths and other subjects, in particular, I'll get on to that in a second. Mechanical toys, apologies. Mechanical toys are also very important. As we know, mechanics is an important part of maths, but it's amazing how little we understand mechanics when we do it. These are Stirling engines, which are toys which look like perpetual motion machines. You get the kid to put their hand out, you put the Stirling engine on their hand, and it goes round. Because the small amount of temperature difference between their hand and the top is enough to expand the air in the chamber and turn the wheel round. And so it's a really, really good way of teaching the mathematics of thermodynamics through mechanical devices, and then you can easily extend that into weather and climate change if you want to. There are many other uses of mechanical toys. Here just a few that we use at our festivals. Jenga, where again you can explore friction, construction, and then there's the famous Euler's disc, which Keith has written a lot about. The back of the back, I think you've written on that. Keith has again. By the way, I don't understand Euler's disc, and I'm far convinced, even from your papers, that we really understand it. But maybe you can. I find it really complicated. Gyroscope. I mean, these are all wonderful things for exploring the fact how interesting mechanics can be, even though we all think Newton wrote down the equations years ago and then it's all done. It's really wonderful how much we can do. Okay, maths and art. So one of the things I love doing is going into schools and doing art with kids but are very much based around mathematics. Now, I'm not an artist, as I say, my daughter is the artist in our family, but I have a really strong interest in the links between maths and art, and one of the links that I love exploring is the maths of Celtic art. And on the left we have the letter T from the Book of Kells. This is, I believe, a lion. I'm not quite sure, it might be a snake. Anyway, some animal. And you have in here this beautiful Celtic knot pattern. And it's wonderful art, it looks beautiful, but I can teach anyone to do one of those using a bit of maths. And then they suddenly think, hey, I can do art, and they can start looking at creativity. And one of the things I really want to get across to kids in schools is that maths is a highly creative subject. I'm sorry to say that maths is often not taught as a creative subject, but of course we all know that it's a highly creative subject. It may be a different type of creativity from art and stuff, although I'm not even sure about that, but there's this wonderful thing. So here we have, on the left, we have the Book of Kells. This is an African knot pattern, and underneath we have a Celtic knot pattern, a simple Celtic knot. How do you draw Celtic knots? Well, if you want to draw a simple one, you do a grid. In this case, it's a grid of 6 lines that way and 5 lines this way. You do crosses on the halves here. You do opposite crosses on the half verticals, and then you join them up, and you get that pattern. So you can teach that very quickly, and you can immediately start producing something nice. And there we are. I mean, that's pretty. Okay, it's not wonderfully creative, but it's pretty, and it gets the kids interested, and you leave them for a month to go away and think. Here's a question. If I made that as a basket with pieces of string, how many pieces of string would I need to create that? Any ideas?
4.
4. Right. 4 are needed for that. Okay. I went to the Pan-African Congress of Mathematics some years ago and was talking about all this stuff in Tunisia, and then I was told that, okay, Celtic art's old, but African art's much older, but basically works along similar lines. And these are examples of things called sonar patterns, which come from sub-Saharan Africa, where you put dots, and then you draw around the dots with your finger, typically in the sand or the earth, and you get these beautiful patterns. These are very, very simple patterns. And mathematically, they're very, very similar. Again, you can teach these kind of toy type of art type things to young people. And how many lines is the question. And you can then do an investigation where the young people explore how many lines are. You all came up with 4 with that. 4 is the highest common factor, 4 and 8. The highest common factor of 3 and 4 is 1. You find there's 1 line. The highest common factor of 2 and 4 is 2. After a certain amount of exploration, young people will come up with that, and then you ask them why. And that will keep them going for years. Okay. By the way, it's Euclid's algorithm, if anyone wants to know. So that's my contribution to maths and art, but the way I do this is get the young people to, I do a session with them, leave them for a month, and then after a month they show me their artistic creations, and they often do it in collaboration with the art department, and we have such fun. Big toys. This is my dog Benji, in front of a labyrinth in Bristol, and the thing about big toys is that they are literally big, and you can get whole groups of people collaborating together to build them. This is the Minotaur, drawn by Chris Sanguine in the audience. There we are. In front of a Cretan labyrinth. The Cretan labyrinth is a geometrical design that you see in many cultures. You see it not only in the Western cultures, but certainly in North American indigenous people have the same diagram. Why do they have it? Presumably because they've been doing mathematical explorations and have found it by a process of discovery, like we all do. The Cretan labyrinth is what's called a unicursal thing, in that there's only one way into the centre, but you go through this kind of complicated route. And by doing this with young people, you can tell them a bit about history, because this idea goes back so far, a bit about fractals and universal diagrams. If you move forward in time to modern mazes like the Hampton Court maze, the idea there is to challenge the young people to think of algorithms for solving this, and then show how you can do these with network theory, how that links to the internet, and many other things like that. But much more fun in doing these papers to actually build one. This is a labyrinth at the University of Kent. This is Liz Mansfield in the middle, and you can see all this. And if any of you are going back through the underground, please have a look on the walls, because on the walls of the underground now, they have labyrinths. We had a collaboration with the underground in 2013, putting up labyrinths on the walls. This is Mark Wallinger, who was the artist that we work with. Mark Wallinger is a Turner Prize winning artist. He has the distinction of being a pointless answer on Pointless when they asked to name Turner Prize winning artists. But he's actually a very good artist, and on all of the walls of the underground you'll find a different labyrinth for the 275 stations in the underground. And to celebrate the fact we're in the Isaac Newton Institute, this is one of the posters. Was it you that commissioned these, Keith? Yeah. Back in the year 2000, and that's the circle line, which is Keith's design, done as a maze. So these are big projects, and again you can teach math through that. Moving on to another, skip that one, chaotic toys, and I can partly thank Michael Berry for this. Here's this picture of me with this young man, and we're doing a card trick, but over here we have some chaotic machines which basically behave in a fairly random way. And the discovery or popularization of chaos seems to have led to a whole new industry in the toy department. If you watch University Challenge, there are the two teams. Who cares about them? Who cares about Jeremy Paxman? Much more interesting, in the front is a chaos machine, which you can have a look at next time you watch University Challenge. And chaos machines are toys which have unpredictable behaviour, essentially because they're based around mechanical systems which have unpredictable chaotic behaviour. And we now know that chaos is endemic in many, many mechanical systems. So what is it? Chaos is complicated behaviour, seemingly complicated behaviour, which comes out of a predictable system. It's very important in many areas of maths and physics. My own area I'm interested in a lot at the moment is weather forecasting, but many others. And for some reason I don't fully understand, maybe the artists in the audience will tell me more, there seems to be a kind of resonance between seeing unpredictable motion with toys and something that human beings like watching. I would have brought a chaos machine with me. Sadly, I've been in Ireland all week, and chaos machines and carry-on baggage for aeroplanes don't go very well together, I've discovered in the past. Just a bit of maths. The maths behind chaos machines, 2 minutes. Okay, I'll skip the maths. And, just to say, if you're in Bristol, do go to St Mary Redcliffe Church, where there's this wonderful chaos machine in the church based on water. It's a water pendulum. Please go and see it. It's wonderful. St Mary Redcliffe is by the station. No excuses. I'll just finish with a little quick bit on mathematical toys. One of the other projects that I've been involved with is trying to teach climate change to young people. Really complicated subject, climate change. There are the equations. Well, that's a subset of the equations. If I stood in front of an audience of young people, or even undergraduates, or even older, they would not be very excited by these equations. I still put them in front of them because I think it's important to see equations. How do we understand and teach climate change? One way is through toy models. And a toy model for climate change, which actually is not bad, is you look at heat from the sun, heating up the earth, radiating into space. You do a balance between heat coming from the sun, heat radiated away, you get this equation. That's your toy model. You can solve it. It's actually pretty good. Gives you the temperature of the earth, and the kids can even work out the temperature from the moon from it. Isn't that amazing? They can find the temperature of the moon from a toy equation, which is a toy model of a very, very complicated system. It blows their minds. Okay, I've run out of time. Just to say in conclusion, toys are a wonderful way for awakening our sense of mathematical curiosity. I argue that they work at all ages and for all levels of ability. And the main thing is just to have fun. Thanks very much.
Are there any questions? Yes.
I've always thought that the phrase toy model, we all know what it means, but it has a very disparaging sound.
Yes.
And I found out that the philosopher, Bob Batterman, who's examined the concept in great detail, thinks the same, and he prefers the term minimal model,
Yes.
which captures the idea. I mean, it's not a strong point, but, but there is something,
I mean, I often use the word reduced model.
yeah, the same.
But the word toy model is often used.
I know, we can't change it, but
Yeah,
it's just...
yeah. But it is a miniature version of a complicated system, so it fits into my definition.
Whatever,
Yeah.
Question? Yes.
Yeah, Dashi.
Just a comment, but I think sometimes the model should be a toy model in the sense that in a map whose scale is 1-to-1 is not useful.
Yes. Yes. Well, a famous quote from, I think it was Einstein, a model should be as simple as possible and no simpler. The question is quite knowing how simple that should be. Yes.
The lower left corner, this odd-shaped dice, what are those?
So these are this is a game, various types of games you can get. They're just dice with different numbers of sides. So one of the questions I ask young people is, can you design me a dice with 31 sides? And by the way, you can.
I was reading that the Romans had them, the icosahedra, is it the 20-sided?
Yeah, 20 sides easy, 31.
Yeah, I'll go home and try that.
Have a think, can you design a fair dice with 31 sides?
But it's a fair day.
Completely fair. 31 sides.
First, yeah.
I'll leave you to think about that in the next talk. Yes.
I do a lot of outreach too, and one of the things we notice when we do events for people is that the adults will bring their children to be entertained, but it's really difficult to engage the adults.
Yeah.
And the second thing we notice is that it's always the same adults, about a subset of the population who show up to these things.
Yeah.
And so while you're outreaching, you tend to outreach to the same 20% of the population all the time, and it's very difficult to get everybody else to show up.
Break the loop.
What we do in Bath is we set up our stalls literally in the centre of town, and we set them up in the car park of the supermarket. So you get a lot of passing trade, and offer free food.
All right. Well, let's thank this again.